Hello and welcome to this presentation. I am Mridu Sungra. I will present my work on deep learning for robotic grasping, which I completed as a part of MS project under the supervision of Dr. Anh Nguyen. I will start with the aim and objectives of the project, a brief description, the output obtained, followed by the evaluation methodology and metrics to qualify my work. The aim of this project is to develop a computer vision based method which uses deep learning techniques and shall be used for autonomous grasping applications. The objectives set forth are to detect objects using object instance segmentation in a scene captured using webcam, uh, then extract the principal axis for grasping each detected object, simulate a UR5 robot using RVIS, demonstrate grasping using a real UR5 robotic hand, and finally test and evaluate the detection and grasping. Applications of robotic grasping techniques are quite widespread, ranging from tedious factory tasks or trivial tasks in houses or hazardous environment like nuclear power plant. So the current work is an attempt to gain an understanding in this important field. For completing the required objectives, this project is divided into three steps. The first is object detection using a pre-trained mask RCNN by PyTorch. An example is shown here on the screen along with the segmentation output. Here the images are captured using my laptop webcam. The second step is to extract the grasping location. This is done by evaluating the principal eigenvector of the masks of the identified object. It is then used to calculate the robot pose, which is published on the corresponding ROS topic. The third step is to implement the result on a real physical robot hardware, which shall grasp the detected object along the identified axis. The robot used is UR5E, controlled using Move-It motion planning system. Coming to the output of this project, first I have demonstrated object instance segmentation using webcam input. In the real physical hardware, the input is acquired using Intel RealSense camera. Second, I have estimated the grasping pose from the eigenvector of the target object mask, which is later published on Vision Post topic. This is done by finding the eigenvector of the target and then calculating its angle from the reference axis and using that angle to evaluate the target pose. I have successfully simulated the robot in RVIS and controlled the real UR5 using MoveIt. In this process, I have learned robot operating system, publishing message on a ROS topic, and then subscribing to the topic to achieve tasks such as grasping. Remaining outputs achieved during this work are the modifications that I have made in the GitHub repository. I have added the provision to grasp the identified object in a single run, where before the vision code was required to run each time a new object is targeted for grasping. I've added some detail about it in the following slides. Additionally, I've added documentation in the repository for running the simulation in RViz as well as the real robot. I've also created a launch file for UR5 and Robot IQ assembly using their respective Zacro files. I've launched the assembly in RViz and I'm able to control it using the interface. To the evaluation part, starting with detection accuracy. For the grasping experiments, only the objects in COCO dataset are used on which the model is trained. The model accurately detects all the objects and with some difficulty even transparent objects such as this fine glass. Very few minor exceptions have been noted, such as misclassification due to clustering of the objects or due to different lighting conditions. For example, this combination here is identified as a handbag, and the effect of lightning has caused this cell phone to be identified as a cup. This issue doesn't really matter for the purpose of experiments, but might have to be addressed in practical cases such as domestic robots for house help or robot which might have to work in different light conditions. I have used 12 of the COCO objects to evaluate robotic grasping. A total of 19 grasping attempts have been made. A second grasping attempt is made for objects which fail in the first attempt, which was case for quite a few objects, such as scissor, toothbrush, and spoon. The details have been added in the demonstration video. Out of the 19 attempts, 10 grasps were successful, which imply a success rate of 52.63%. Out of all the successful grasps, 7 were stable. The 3 unstable are demonstrated in this video. So these grasps were not able to satisfy the force closure property. Execution time implies the time from planning after pose estimation for grasp till the time the object is released. The average time of the 10 successful picks is around 25 seconds. It includes the time to plan and execute the grasp. Mean pick per hour is around 80. This includes the sleep time between each grasp, which allow the vision system to perform segmentation on the input camera image and publish the pose. Without this sleep time, it was observed that the robot assumed the pose it calculated for its previous grasping attempt. To summarize, through this project work, I have demonstrated use of robot operating system. I have used it to implement autonomous robotic grasping. The system has achieved a grasping success rate of 52.63%, out of which 70% grasps have been established as a stable grasp. Following all this, I've updated the GitHub repository for this project work. So that is all from my side. Thank you.